Can you just read out the question?
Yeah, sure. Okay, so circle a stronger acid, which was CH3CH2OH, and then the other one was CH3COH.
All right, this is for the kinetics?
Yes.
Yeah.
Okay, that's not going to be on this this test. We haven't.
So the strength of acids and the acids isn't going to be on it?
Yeah, that's after we do the lab. This is usually, we'll do that lab with acid strengths, and we'll talk about acid strengths, the Spartan lab.
Oh, yeah.
And then I put it on the test.
Okay, so we have the next exam if we have it?
Yeah, right.
So the last,
Hopefully they fix Spartan right now.
so the last question is not going to be one to be one, right?
Yeah, the last question was dealing with show the negative charge density on oxygen varies the two constants or the trichloroacetate.
Yeah. Okay. Yeah, that's something I talk about. No, that's something I talk about in the lab. Yeah, it's part of the lab. So those are actually we skipped that section in chapter 16 because it's supposed to officially be covered in Chem 1A, and then we do this lab, and then yeah, it's kind of a review, and then yeah, we test. Normally I do this Spartan lab in Chem 1A for the acids, and then do it for the bases in Chem 1B. Any other questions from that?
Number 9. In enzyme kinetics at a very high substrate concentrations, the reaction is 0%.
A very high substrate concentration means that you have lots of reactant, not that much enzyme. And so if you double the amount of substrate, which is reactant, would you expect the reaction rate to double? No, it probably, yeah, you fairly saturated out all your enzyme, and it's going to be what order? Zero order. Right. And so a high substrate concentration should be zero.
About number 16.
Number 16?
Propose a two-step mechanism. Step 2. Step 2 is limiting one for ozone decomposition.
Okay,
203.
203 goes to 302.
Yeah.
We want a two-step mechanism. You know, looking at this could be a one-step mechanism, right? A one-step mechanism would be two ozones. We have a, what do we call it? Bimolecular collision. So it could be, if this were a one-step mechanism, what would its rate law be? K03 squared. And so if the actual experimental rate law is K03 squared, then it's likely a one-step bimolecular collision. But it turns out the rate law, the experimental rate law, isn't that. It's got to be multi-step. And so we have to propose a mechanism. And so we have different choices. What hint did I give you?
Step 2 is RDS, that's it.
Okay, step 2 is the RDS. So the first step is going to be quick. Okay, so we have some choices here. We could have an ozone collide with an ozone in step 1. Now this would be a bimolecular collision. Or we could have a ozone decompose, like either collide with the wall or some inert gas molecule. And so just an ozone decomposes. Out of these two, which one do you want to start with? Maybe the first one. If we start off with the first one, an ozone collides with an ozone, what can we form? So we try to think of things that, yeah, make sense.
Oxygen.
O2 and
O2,
O2, O2 and O2. That makes sense, but it doesn't happen.
It doesn't make sense to me.
Well, maybe like this. Ozone plus an ozone yields an O plus an O4. How about that?
No.
Does that? No.
1, 2.
It doesn't really make sense. How about an O plus an O plus an O plus an O? No.
Well, yeah.
I see this a lot. O2 minus plus O2 minus. You know, plus. Yeah, you can build up too much negative charge. You have to have some positive charge to balance it out, right? Because you can't just all have negative charge here. This can't be neutral, and this can't be all negative, right? This will be neutral and neutral. So we'll go with O2 plus O2 plus, and that balances out the charge.
Is it possible?
No, this is not.
Even though like they have the equal charge, like because you have O2 minus and O2 plus.
Yeah, that's possible, but it would be very short-lived. Yeah, it could happen. Yeah, it's possible.
So how can we know, like, is it right or wrong? What
Well,
do you
that you know, if you get an O2 minus and an O2 plus, that would be a pretty slow step you'd expect. Or you just wouldn't form much of it. And so we run out of possibilities there. Maybe ozone. Ozone hits the wall and breaks up into, what do you think? O2 and an O. Then in the next step, O reacts with a ozone to produce 2 O2s. All right. So this would be a fast reversible. Ozone is highly reactive, so maybe you'd expect it to decompose quickly. It doesn't last for too terribly long. And then maybe this is the slow step, but you know, you think atomic oxygen is very reactive. But the atomic oxygen could be attacking other things. It's just got to find an ozone to attack. And then maybe this is the slow, the RDS. And so this could work because the net reaction adds up. You know, 2 ozones yields 3 O2s. The oxygens cancel out. But the rate law has to match. Right? What was the rate?
You're doing steady state.
Okay, using steady, did I say derive it using steady state approximation?
Yeah.
All right. All right, we could derive it. Do you want to do that, or is this?
Yeah, let's do it.
Yeah.
And so the rate for the RDF is just equal to the K.
P2.
Actually, yeah, this would be K2. K2 times the oxygen to the first and the ozone to the first. That was first order in oxygen, first order in ozone.
Is it first order because of the coefficient?
Hmm?
Is it first order
Because of the coefficients. These are all elementary processes. Yeah. Then, if we do the steady state, then the rate of, you know, O production, actually, we'll just leave it, is equal to the rate of O consumption. So the rate of O production, how's O being produced? Just from K1, it looks like. K1 times ozone. It's first order in ozone. How's O being consumed? Well, K minus 1, you know, the reverse process, times O2 to the first, O to the first, plus K2, O, O3. So we can factor out the O here and then just solve for that. The O is going to equal K1 times the ozone first over K minus 1 times the O2 plus K2 times the O3. Is that right? Is that correct? Okay, then we substitute that. back into the rate law. And so the rate should equal K2 times all that stuff, which is K1 ozone over K minus 1 O2 plus K2 O3 times the O3. So this is going to equal, we'll just call it K prime, which will be K2 times K1 times O3 squared over the K minus 1 O2 plus K2 O3. All right, now with this, O2 appears in here, but is it okay to have O2 in here? We can't have an intermediate, but this is not an intermediate. You know, this is product. Having product in here is okay. Because what happens is we get this, we call this negative feedback, you know, or this inhibition. In other words, what happens as the product concentration goes up? As the product concentration increases, gets bigger and bigger, the rate of the reaction should decrease. And so that's what the negative feedback is. The more product there, the slower the rate. And then it has this weird order. I mean, if K2, that is this leakage here off K2, the consumption, is very slow, then this term is quite small. If this term is quite small, then this becomes negligible. And so this becomes second order. Is that right? Second order in ozone?
Yes.
And negative one order in O2? Yeah. If this step becomes increasingly large, then it would be more like first order. That's all we can say. What did I give you the experimental? No.
So it'd just be, that would be the answer.
That would be the answer. Yeah. That's it. We can't do much, you know, for calculations with these more complicated rate laws. We don't really do any time or concentration calculations. They're too complex. The only thing we do timing and concentration calculations for are single reactant reactions, you know, these decompositions, or pseudo single reactant reactions. And there we can get the integrated rate law. But we aren't going to get the integrated rate law when we have these things. And so we always just leave it at this. We don't do much beyond this.
What is the difference between steady state approximation and the other one that we just use the rate forward equal rate reverse? So we didn't add to K2 at all. So what is the difference?
The difference between fast reversible
Yeah.
and steady state? Fast reversible is just a simplification of the steady state approximation. The steady state approximation assumes this term K2 is very small, so we don't lose that much intermediate this way. And so if this term's small, then we can kind of ignore it, and that would be the rate law.
So if we forgot to, like, you say steady state and like suddenly just do fast reversible, it's still right?
No. If I ask you to do steady state and you do fast reversible, it's not right.
No, but they
Because the steady, if you did fast reversible and this term drops out, well, let's say if this term is large, K2 is large, then it's going to be wrong. You'll get the wrong order here. you ask what's the difference between fast reversible and steady state, it's kind of the same thing. You know, you're just making an assumption. Some people ask, what's the difference between classical physics and quantum physics? It turns out like classical physics is the same thing, except you're making an assumption. You assume that, what? Well, or you restrict it. You know, classical physics is the same thing as quantum physics as long as you make a restriction. You know what the restriction is? In other words, you can derive all the laws of classical physics, all Newton's laws, if you restrict quantum physics to large objects. You know, large objects where the wavelength is not going to, de Broglie and Heisenberg, that kind of stuff, aren't going to. You know, the uncertainty is so small in large objects. All right, other questions?
Can you read number 67?
Number 67. What's number 67?
By mechanism, the reaction leaves like 2 NO plus 2 hydrogen. The product CN2 plus 2 water. And mix
What is it asking for?
they say like the second step, I mean the second order in NO and the third order in hydrogen.
Okay.
And they ask to propose 3 steps of mechanism.
Second order in NO,
Yes, and the third order in hydrogen.
first order in hydrogen, and they want what, 3-step?
Yeah. The first step is fast step.
First step is fast?
Yeah. The third also fast too.
First and third are fast,
Yes.
and so the second is slow.
Yeah.
All right. So we have some choices here. It could be unimolecular. NO decomposes. You know, NO, what would it decompose into? Well, no, just NO decompose. Unimolecular. Let's try it. NO unimolecular decomposes into N plus O, or what? An N3 minus plus an O2 minus?
No.
No, this is impossible. Everybody see that? Well, maybe an N2 plus and an O2 minus. How about that?
No.
Does that look very likely? Out of these, which one looks most likely? The first one. We can't go to an N2 and an O2 because we need 2 NOs to do that. This is just a unimolecular,
Oh, yeah.
right? And so this has to collide with the wall or something and break the bond. Do you think that bond is very strong, the NO bond? It's a triple bond. It's going to be strong. So this is not going to be a fast step. This is going to be a slow step. Yeah. I said fast, so yeah, this just doesn't seem like it's going to happen. H2 unimolecular. You know, H2 collides with the wall to form 2 hydrogen atoms. What do you think about that? Or maybe an H plus and an H minus. This could happen, but what do you think about the stability of something like this? You know, if there's a tug of war between 2 hydrogens, who's going to win? The right hydrogen? Right hydrogen is stronger than the left hydrogen? No, and so this is terribly unstable, right? And so that could happen, but you think that's very reasonable? No. All right, then let's try maybe an NO plus an H2. What can we form with an NO and an H2? Maybe an HNO. Have you heard of this acid, HNO plus an H.
No, not like that.
The nitrous acid is HNO2. What is HNO? Have you ever heard of it? Hyponitrous, maybe? Yeah. Have you ever heard of hyponitrite? No, never heard of hyponitrite. So, I mean, maybe, but let's try something else.
Can we form an atom of hydrogen?
H2NO, diprotic.
No,
Acid, no.
just
So what should we try next?
Water and
NO plus NO.
We can't do water because water is a product. And it can only take reactants. So NO plus NO would yield
And two also.
N2 plus O2. But you know, one thing about N2 and O2 is are they very reactive? No. And so on the one hand, this is good because we're forming a stable mixture. On the other hand, you know, oh, actually we do have N2 here. Yeah, so this might work. Because if we got the N2 here, and then all we have to do is form the water, which is O2 plus 2H2, this will give me 2H2O.
But this is 3 steps.
Yeah, this has got to be 3 steps, so it's not going to work then.
Can we form all the products from N2 and N2?
Unless I do, wait, if I do this, if I do an H2 plus an O2 yields an H2O plus an O. And then have the second O attack the other H2. Maybe that might. But hydrogen and oxygen, is that a slow reaction? You think the second step, hydrogen and oxygen, is that, you think, a slow reaction or? No, the hydrogen and oxygen, you know, explosives depends on how much energy is produced and how fast the reaction is. You know, whether it's something like it's a very, very accelerated combustion, or something that actually detonates and creates some kind of shock wave. You know, hydrogen and oxygen react very rapidly. And so I wouldn't expect this to be very slow. You know. And so let's try something else. Maybe. What else could we try? Well, NO plus an NO might yield N2O2. There are a whole bunch of different oxides of nitrogen, like nitrous oxide, N2O, you know, nitric oxide, NO, nitrogen dioxide, you know. Hold on, so this is dinitrogen dioxide. There's also dinitrogen tetroxide. So there's a whole bunch of different oxides of nitrogen. And so this might happen fast. You know, 2 NOs combined. You just got to link them together, break some bonds, form some bonds. And then the N2O2 reacts with what? Plus, well, we got to get rid of one hydrogen. If we form a water, then that leaves us with a N2O. N2O is known as dinitrogen monoxide, or this one's called nitrous oxide. N2O. Nitrous oxide. And then maybe this nitrous oxide plus another H2 could produce another water plus N2. Yeah, that might work. Nitrous oxide, this one is a favorite in Chem 1A. Why? because of the Lewis structure. Do you guys remember doing nitrous oxide? What was the Lewis structure? Was it triple bond? Or was it two double bonds? You guys remember? I don't know if everybody did this, but typically this is one of the favorites in Chem 1A because which one do you think is more stable? The two double bonds or the triple single? Or we could also do this triple and this single. This one doesn't look good, right? Why? The formal charges. This one has the worst. The formal charges are very bad. So we eliminate this one. And we have these two. Which one's better? Hmm? Yeah, the hybrids. There you go. There you go. But anyway, which one's better? The one on the top. Why? Because the negative formal charge is on oxygen rather than nitrogen. But, you know, we can't say that this one is going to dominate because oxygen and nitrogen, is there a clear winner? If there's a tug of war between oxygen and nitrogen, you know, they're close. Oxygen is a 3,5, nitrogen is a 3,0. So they're close, which means that, yeah, it's something in between, but it's going to bias oxygen, which means that we have the inequivalent resonance forms, and our hybrid was going to be biased towards this one. Well, so you've seen nitrous oxide before, and so this seems reasonable, and it's probably slow because mechanistically this doesn't look so easy. Same thing with this, but let's assume that this were it. If this were it, well, we could also eliminate a lot of these other ones based on the rate law that we would have derived. Let's say we went with this one. We generated the rate law. The rate law is not going to match an experiment. But we were able to eliminate this based on other things, like this. This hydrogen and oxygen react explosively, right? And then this is a weird product, atomic oxygen here. Well, anyway, if we go with this one and we say that the rate is equal to dinitrogen dioxide, the first, hydrogen to the first, and then we get rid of this, you know, using the fast reversible, then what would we end up with? We end up with this. Does everybody see that, or do you want to work through? Work through.
How we compare which one is faster?
What's that?
How do we know that which one is faster than the other?
I'm just guessing.
Is it the true answer?
Hmm?
Is it the right answer, like just guessing, or
Is it the right answer? You know, people want to take more of the guesswork out, so they'll do some calculations to figure out
so just do the calculation?
which transition states would make sense. You know, these are all simple collisions, so they're going to go through some kind of transition state, right? And you want to go through, or you want to try to find the path of least, you know, resistance. And so you can do some calculations, figure out what the transition state of this looks like. You know, the transition state of this might look something like this. Calculate, you know, how big of a hump that would be. And then figure out other transition states. Then do this for all the other potential. You know, it's not total guessing because you got to figure out what seems to be a reasonable collision. What's for us, we're just guessing. How do I know? You just make an assumption, try it. If it fails, then try a new guess. You know, it's the guess and check method of kinetics. Okay, so we got this, and then the rate for the RDS is equal to K2 N2O2 times H2. And then we do fast reversible here. If we do fast reversible, then K1 times NO squared is equal to K minus 1 times N2O2. And therefore, the N2O2 is equal to K1 over K minus 1 NO squared. So we'll just plug that in here. That's K1 over K minus 1 NO squared H2, which gives us K2 K1 over K minus 1 NO squared H2, which is just K prime NO squared H2. So second order in NO, first order in H2, which happens to agree with this. This is experimental fact. And so whatever our theory is, it has to agree with experimental fact, because if our theory doesn't agree, then which one's wrong? The theory. And so here, unless there's some experimental errors.
So for this problem, we didn't use the third equation at all.
No, we don't use the third equation because it doesn't matter.
Is it there?
The only time the third equation would matter is if there's intermediate. Let's say there's two competing reactions. There's N2O2 here, and there's N2O2 here. Then it matters. Because when we do the steady state, then the N2O2 can be consumed K minus 1, it can be consumed K2, and it can be consumed K3. And then it would matter, because we have to compensate for the consumption there. But otherwise, it doesn't matter if it's 50 steps. If you have a 50-step mechanism and the first step is the slowest, then the rate is just going to be dictated by the first step. So it matches, which means that this must be correct. Yes? True or false? This must be correct. False. Why is that false?
Can you just observe? You didn't do any experiment?
No, that's not the reason. I mean, we do need to do some experiment, but you should phrase it in a different way.
Is it not the only way to get that?
Yeah, it might not be the only mechanism that yields this rate law. And so there could be other potential mechanisms there that would yield a similar rate law. And so the only thing you can say is that what?
This may be right.
Yeah, and this is, the only thing you can say is that it is
Not the only one.
consistent with the experimental data. And so this mechanism is consistent with the experimental data. You can't say this mechanism is the correct mechanism, but it is consistent, so it's possible this could happen. And more experiments could help, like determining if indeed dinitrogen dioxide forms. If dinitrogen dioxide forms and is consumed, then it's good evidence. Other ways, people try to use these ultra-fast lasers. Because how fast does a reaction like this occur? 1 minute you see NO, the next minute you see N2O2. But with these ultra-fast lasers, like femtosecond lasers, you ever heard of those? They might even have, I think they have faster than femto. What's faster than femtosecond? You know what's faster than a femtosecond? what is it, nanosecond? And then what comes after nanosecond? Picosecond. Picosecond is micro is 10 to the minus 6. Nano is 10 to the minus 9. Pico is 10 to the minus 12. So femto is 10 to the minus 15. So that's 10 to the 15 counts per second. Or, can you believe that? How fast that is?
How do you spell femto?
FEMPTO. A femtosecond laser can probe this so fast that it could observe the transition state. The transition state is not the same thing in the intermediate. Something like an intermediate is going to last for some time, N2O2, because this is slow step. The slow step's consuming that intermediate. And so this is an intermediate product. But a transition state like this, how long does that last? It's this precarious state. And so with these ultra-fast lasers, they can probe this and see what's happening with electron density distribution, by the signals it gives off. And so that's another way they're looking at it. They want to see how the reactions happen, in as much step-to-step detail as possible. The gas phase reaction. Other questions? So are you guys ready for the chapter 14? Not at all?
Yeah.
Almost.
Is there an answer key for the practice test that you put out there?
Yeah, but if I put out the answer key, it's not a realistic simulation of the test. I want something where you think, how do you know you got the right answer? This is a problem because a lot of people, when they get their answer, they check it against the key, the answer key. And if it's right, then great. If it's wrong, then they go back and fix it. But the problem is they don't develop this habit where they go back and double check their calculations or double check their answers. I don't double check because I expect you guys to check all my work. But you should on an exam. How do you know? Because so many people could have made a lot more points on the test if they just recheck their calculation. A lot of people have the setup correct. They just made a calculator error, miskeyed or did something. And so I try to take off minimal, but that's not always the case because, I've worked with a lot of different professors, and some professors, it's either right or wrong. If you got the wrong answer, they give you 0 credit, which means that you're all of a sudden, it's a bimodal curve. A whole bunch of people fail, a whole bunch of people do okay. And so you got to start, checking. And then when you check those, you also check your work and your thinking, and you go, okay, this sounds right. And then what you want to do is you want to build that confidence in yourself, that, I checked this, it looks right to me, and then I'm sure I have the right answer. You want to get that level of confidence in your answer, if it's possible. Such to the point where you can catch errors, like in the book. The book did this wrong, or when I do something, you did something wrong here, because you go through it, you check it, you self-check it, and that kind of thing. And so I stopped, and the other reason that's one of the reasons I do have the answer key, and so if the persistence, but a lot of people just study the practice test, and that's it. And if that's the case, then I'm going to make a test, totally 180, different than the practice test, and then it loses its effectiveness, So you want to study a little bit more than practice test. What's on?
92.
92?
iodine, they give like EI and a big bang. That would be on
Okay, enzyme plus inhibitor.
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 What is
Enzyme plus inhibitor.
study the catalyst? What is
The rate of an enzyme catalyzed reaction can be slowed down by the presence of an inhibitor. What does it say? That reacts with the enzyme in a rapid equilibrium process. By adding this step to the mechanism for enzyme catalysis, on page 641, determine the effect of adding the concentration I0 on the rate of an enzyme catalyzed reaction. So, then we need this enzyme, right? Enzyme plus substrate is going to give us the enzyme substrate. And then the enzyme substrate is going to decompose into enzyme plus a product. And so we just add this step to this. Now, basically what this does is it means that there's going to be competition for enzyme. Here, inhibitor and substrate. And so that means that we have to factor all this in. And so something like this, something like this, I don't necessarily expect you to derive. This I just wanted you to take a look at and see how an inhibitor would impact the concentration. And so you really don't have to worry too much. It's just the more inhibitor that we put in here, it should, less reaction. That's it. Yeah, right, because now the enzyme is going to have some competition. The inhibitor. And the inhibitor isn't going to lead to it. And if it's a very strong inhibitor, then it's going to disable the enzyme. And so I put this in thinking that you could just look at the answer and the solutions guide and then see, that's how it's done. But not necessarily to derive. And so I don't want to spend too much time. Although you could figure it out. Any other questions? No. The same thing with the other You know, there was another problem. You know, when you were asking me about step 2 or step 3, you know, can we ignore step 3? If step 2 is the RDS. And there's one problem in your homework where we can't ignore step 3 because the intermediate was consumed in step 3. Did you see that one? The intermediate is consumed both in step 2 and step 3. That one you just look for your reference. I probably wouldn't throw on the test. I have put that on the test before. So, What's that? No, I won't. I have put that on the test, but only 2 people got it right, and everybody else got it wrong. And so it wasn't very good question. And people stayed very late. I don't want to stay too late. That happens when people are trying to figure out the mechanisms and end up going an hour over, hour and a half over. So I learned. Try to do something more reasonable. But still, I wanted to throw those in the homework just so you'd see those. All right, if there are no other questions, then let's talk about some new stuff. If something else comes up, let me know. So let's talk about the second law of thermodynamics. Now, the second law just says that the delta S of the universe should be greater than 0 for spontaneous. It's going to equal 0 or less than 0 for non-spontaneous. There's another way. This is too difficult to determine, so we can get delta S of the universe in this form, looking at the Gibbs free energy, which is G. Gibbs free energy. And so we look at the change in the Gibbs free energy, which is going to be related to delta H minus T delta S. This is good because this is all in terms of the system. And so we can see if this is less than 0, then it should be spontaneous. If it's equal to 0, it's at equilibrium. And if it's greater than 0, it's non-spontaneous. When we say non-spontaneous here, the reverse reaction is spontaneous. And so delta G is a way to figure it out. And in terms of this, you know, what's favorable? Favorable is we want to minimize energy. That is, you know, we want enthalpy to go down, energy to go down. And when energy goes down, then delta H is negative. That's favorable. And we want to maximize entropy. Maximize S. So it should be positive. And so temperature is always positive. So it's positive times positive and give us a negative here. And so how is the energy related back to the entropy of the universe? What do you say? Is the energy related to the entropy of the universe? Yeah. In what way is the energy related to the entropy of the universe?
Decreases in entropy.
If we have an exothermic reaction, how does the entropy of the universe increase if we have an exothermic reaction? Because did you know that the total energy of the universe is fixed? It's not zero, but it's fixed. Because energy can neither be created nor destroyed. And so the total energy of the universe, delta E of the universe, the total energy is fixed. Therefore, the universe, if we look at the energy of the universe as a whole, does it ever change? No. So delta E of the universe is always zero. Right? So if something loses energy, something else gains energy, and we end up with like the zero sum. The energy of the universe is constant. So if the energy of the universe is constant, what's driving things? What's driving things is entropy. The entropy of the universe is always increasing. Once the entropy of the universe stops increasing, then there's no more driving force for anything, which means that, no more reactions are going to occur. So, the entropy of the universe is constantly increasing. Otherwise, nothing would happen. And the energy of the universe isn't constantly decreasing. The energy of the universe is fixed. And so when we lose energy of the system, the energy still goes somewhere. Where did that energy go? It went into the surroundings. So the net energy, does net energy change for the system? Yes, minus. But the surroundings got a boost, positive, and so the total is zero. Q of the system is equal to minus Q of the surroundings. Q of the system plus Q of the surroundings is equal to zero. But this also results in an increase in the entropy of the universe, because if we have an exothermic reaction, then we're converting chemical potential energy into kinetic energy or heat. And chemical potential energy is a more ordered form of energy versus heat, which is a much more disordered form of energy. And so that's how we can see. And so both of these are saying the same thing. When we minimize energy, that's increasing the entropy, right? Increasing entropy of the universe. Yes. All right, now let's use this. To use this equation is not difficult because, delta H we can calculate, delta S we can calculate. But this is not the easiest way to determine delta G. Do you know what the easiest way to determine delta G is? The easiest way to determine delta G is by using delta G as a formation. So if we want some delta G of some reaction, all we do is we sum up the mu P, which means the moles of product, times delta G of formation for the product, minus the sum of, mu R times delta G of formation of the reactant. And so it's just the delta G's of the formation of the products minus delta G's of the formation of the reactants. Where do we get these? Delta G's of formation? These are in Appendix D. And so this is the easiest method for calculating delta G. But you have to be aware there are some restrictions on this. What are the restrictions if we use Appendix D data? Yeah. The restrictions for Appendix D are we need 1 molar solutions. 2, we need 1 bar or 1 atm pressures for the gases. 3, is there another restriction on Appendix D? Yes, room temperature, 298 Kelvin. Appendix D data is valid only at 298 Kelvin. So the entropy is there. And so we have these restrictions. And if we're okay with these restrictions, then this is the easiest way. But let's say I want delta G at a different temperature, because temperature can impact the spontaneity of reactions. Some reactions are spontaneous at high temperatures and non-spontaneous at low, and vice versa. And so sometimes we can alter the temperature and change our driving force. But in this case, we're stuck. This is the driving force at 298 Kelvin. That's all we're going to get. And so this equation is more calculation, but this equation does have some additional power. What additional function does this equation have that equation doesn't? This equation has temperature as a variable there, which means we can change the temperature. And so if we change the temperature, you can see delta G will change. For sure it's going to change. But if we change the temperature on that equation, there's one problem, because we get delta H from appendix D, and we get delta S from appendix D, typically. We need the delta H and the delta S value at that new temperature, right? And so this one is more powerful because we can change the temperature. But on the other hand, this is delta G of the system at any temperature, T, which is going to equal delta H of the system at any temperature T minus T delta S of the system at temperature T. So as long as we have this, if we're given in the book delta H at, let's say, 500 degrees C is this, delta S at 500 degrees C is this, and then the temperature, 500 degrees C converted to Kelvin, that's your temperature. Right? And so if we have the values, all these temperatures need to match, right? And the data needs to match. But we can make an assumption. I made this assumption last time. What was the assumption that I made? If we're missing the delta H and the delta S value at those temperatures, then we might try to substitute. So let's say if delta H at T and delta S at T, temperature T, are unknown, then try this. Then try to use what? Try to use this assumption. As long as the state is the same, then what we're going to do is we're going to just say delta H at temperature T, whatever temperature that is going to be approximately equal to delta H at 298 Kelvin. And delta S at some temperature T will be approximately equal to delta S at 298 Kelvin. And then we can solve it. If we have the value, that would be better. Because if we have the value, then we can calculate a more accurate answer. And so let's go ahead and try out a calculation here. Let's look at this. H2O liquid goes to H2O gas. H2O liquid goes to H2O gas let's say delta G at 298. Delta G at 298 would be, what do you think, greater than 0? Equal to 0 or less than 0?
Less than 0.
It's got to be less than 0. Why?
Entropy increases?
No. Well, based on this, we can figure out what delta H is. Delta H is endothermic or exothermic? Endothermic. We're converting a liquid into a gas. It's going to be endothermic. Delta S is going to be increasing. And so what this means is it's spontaneous at high temperature, non-spontaneous at low temperature. Now, what is high temperature? What is low temperature? High temperature and low temperature are just relative to whatever the reaction or process we're looking at. In this case, I know that room temperature would be considered low temperature. Why? Because does water spontaneously boil into a gas at room temperature? No. And so this is just based on factual knowledge for water. So at what temperature would it go? So room temperature is low temperature, and so at what temperature do we convert to high temperature? And so what is high temperature here? Well, high temperature would be where it goes from being non-spontaneous to spontaneous. And so to figure that out, we just need to do some calculations, but we probably don't need any calculations because you probably know when it goes from non-spontaneous to spontaneous. So what temperature does water vaporize spontaneously? 373, right? The boiling point. And so let's do the calculation. I already know the answer.
Mm-hmm. So if delta G is less than 0, it's non-spontaneous?
Yes. Oh.
Because you said
No.
opposite.
Sorry. Delta G is greater than 0. I said the opposite. This is non-spontaneous. Yeah, delta G has to be greater than 0 for non-spontaneous processes. So let's take a look and do a couple of quick calculations to see that delta G is in fact greater than 0. And so I'm going to go to Appendix D data. You know, if you are working on that practice quiz and you really need to know the answer, it's really stumping you, then just post it on Piazza. I'll take a look and then I'll let you know it's correct or incorrect. All right, so let's go to Appendix D. The easiest way to figure out what delta G is by using the delta G's of formation. So we'll do that. Delta G's of formation are going to be the second column here. Units are in kilojoules per mole. And so we're going to go to water, which will be hydrogen. H. So if we look at liquid water, which is a product. Delta G of formation is minus 237.1. We have 1 mole. That would be that many kilojoules. I'm sorry. I want gaseous water. Gaseous water is my product, right? And so that's going to be a minus 228.6 minus a minus 237.1, which gives me a positive. What's that? 8.5? 9.5? 8.5? All right. So using Appendix D data, we just figured out it's going to be plus 8.5 kilojoules as written. And you could write this kilojoules per mole or just kilojoules because it is per mole there. And so this means we have to put this little superscript here. What does that superscript mean? Yeah, not only do I have to have well, this one just reminds me, not only do I have to have this, but I also have to have this, because when I have this little superscript 0 here, it doesn't tell me the temperature. What is the temperature of this? And so normally we have to either keep mental track of this, or we'll just write it down here. This is going to be at 298 Kelvin, so we don't get mixed up. And so that's not good enough. And anyway, it is endothermic, so all we can say is it's non-spontaneous, right? And that was the easiest way. Let's do the other way, which involves more work. Because we have to calculate delta H. The delta H for this process will be the delta H of formation of H2O gas minus the delta H of formation of H2O liquid. And so here we have our gas minus 241.8. Here's our liquid. So it's going to be minus 241.8 minus a minus 285.8, which will be a plus 44.0 kilojoules. So actually that wasn't so bad. Plus 44.0 kilojoules. Okay, again, this is going to be under standard conditions at 298 Kelvin. Okay, now we have to calculate our delta S under standard conditions at 298 Kelvin. So let's do that. Here, it's going to be the entropy of the gas minus the entropy of the liquid. Okay, entropy of the gas here is 33.6. Entropy of the liquid is 75.3. And so it looks like this minus this. No. Is that right? Gas. How can the gas be lower entropy than the liquid? That's wrong, because I'm reading the wrong column. This is the heat capacity. This must be the entropy here. So H2O gas is 188.8 minus 69.91. What does that come out to? Can someone calculate that? 188.8, 69.91. Fortunately, everything's 1 mole, so. 118.89. And the units are going to be in joules per Kelvin. So keep track of that. All right, so now let's go ahead and do our calculation. So delta G under standard conditions at 298 Kelvin will equal a delta H, which is plus 44.0 kilojoules, minus T. T is going to be at 298 Kelvin, times delta S, which is going to be 118.89 joules per Kelvin. Now, we have a problem here because units being in joules, we need to convert it to kilojoules. Let's go ahead and do that. Divided by 1,000. And what does that come out to here? Well, let's first calculate this second term. So this is 44.0 kilojoules minus, can someone just calculate this part? $35.42. 35.42. All right, do you see that the enthalpy dominates here? We need to increase the entropy so that at least it cancels out. This is inhibiting the reaction. This is trying to drive the reaction. And so one way to make this second term grow bigger is to increase the temperature. And so we got to find out at what temperature will this go from being positive to 0 and then negative. And so we need to adjust the temperature here. And so, well, let's go ahead and figure out this. What does it come out to? 8.57. And what did we have before? 8.5. They're supposed to be the same number. They aren't. It's probably sig figs, or a lot of these are experimental numbers, so that could account for the difference. But anyway, let's go ahead and go with this here at 8.57. At the temperature in which this goes from positive to 0 will be when we get 44 minus 44. And to get minus 44 here, we just need to change the temperature. And so we solve for the temperature. The temperature is going to equal well, actually, this is what we'll do. We want delta G naught at 298 Kelvin, or at temperature T. Now, this is no longer at 298. We want delta G naught at temperature T to equal 0. We just have to figure out what that temperature T is. And so this is going to equal delta H naught minus T delta S naught. Solving for the temperature is just going to equal delta H naught over delta S naught. But there's a problem with this. The problem is this delta H naught is supposed to be at temperature T, and this delta S naught is supposed to be at temperature T. And so we have too many unknowns here. And so we're going to make an assumption. What's the assumption we're going to make? Yeah. So we're going to say that this is approximately equal to delta H naught at 298 Kelvin and delta S naught at 298 Kelvin. And so we're just going to use the 298 Kelvin values. So delta H naught is 44.0 kilojoules. Delta S naught is 118 divided by 1,000. So this comes out to 0.1189 kilojoules per Kelvin. And so when we calculate the temperature, it's 44 divided by 0.1189. We get a temperature of, what is it?
370.
370 Kelvin. It's supposed to be 373, but it's close.
I thought you said don't do that if there's a change of state.
Oh, I meant this. I meant that, for example, if you went from H2O, right, this is always going from H2O liquid to H2O gas within a certain temperature range. But let's say if you drop the temperature too low or raise the temperature too high, then what's going to happen is you're going to go from H2O gas to H2O gas if the temperature is too high, or you'll go from H2O solid to H2O liquid if the temperature is too low. And so this is what I meant if there's a change in state of the reactants or a change in state of the products. But if the reactant state stays the same and the product state stays the same, then we're going to use it. Okay. And so it means that there's a limited temperature range in which this assumption works, because I can't say that, let's say the temperature were 1,000 Kelvin. At 1,000 Kelvin, do you expect any liquid water around? No. And so it doesn't work. We can't say that delta H naught at 1,000 Kelvin is the same as delta H naught at 298, because by the time we hit 373, all that liquid's just been converted into gas. So that's what I mean by change of state. Not the process is, you're right, the process is a change of state, so it should have been more clear about that. What I meant was something a little different than that. All right, so what we can do is we can use temperature to control the driving force, because any temperature higher than that will make delta G negative. And so we want temperatures greater than 370 Kelvin to make this spontaneous. And so here, this is one of the major calculations that we can do. We can alter the driving force by changing temperature. Sometimes we can make a spontaneous go non-spontaneous, or non-spontaneous go spontaneous. Sometimes we could just make it less one way or the other. All right, that's this. Now, is there any other way to change the driving force? Yeah, by changing the pressure. By changing the pressure, or by changing the concentration. That will change the driving force. And so what we're going to talk about next is using pressure and or concentration to change delta G. When we change pressure or concentration, that's called non-standard conditions. Because standard conditions, the pressure and the concentration are fixed. And so when we go non-standard, how do we deal with non-standard conditions? So we'll talk about that next time. So I'll stop here for now. But if you have some more questions on chapter 14 stuff, I'll be here.